Welcome to our IMTS 2022 press conference. I think I know many of you already, but for those of you I've not had the pleasure to meet, my name is John Meyer. I'm the Marketing Communications Manager for the motion control and the machine tool business here in the United States. We appreciate the time you've taken to be with us today, and we hope you will find a lot of valuable information that you can take home from the press conference that is going to be really of great interest to the readers of your publications. All of the information that you will hear about today will be in the press kit that we'll hand out at the conclusion of the event. Before we get started, I'd like to cover really quickly just 4 topics that we'll talk about and present today. Firstly, my colleague Chris Pollock, he'll talk about the newest innovations in machine tool CNC technology. Many of you have already heard of and are familiar with our new control platform, Sinumerik One. Well, Chris will talk a little bit more in detail about the new control, as well as the digital twin. Next, my colleagues Vivek Furtado and Dave Morley will continue the digital twin topic by going further into detail about the newest machine tool digitalization software elements that really comprise the entire topic. Then, Tim Bell, he'll talk about the additive manufacturing industry and how CNC and digitalization technology, how they really play these important roles in this very important manufacturing segment. And lastly, my colleague Vince Paradise will discuss how all of these elements fit inside the new Siemens Xcelerator portfolio. So without further ado, I invite Chris to come up to the stage.
Thank you, John. I appreciate that. Those are your claps, John, not mine yet, but it's coming. So thanks again, everybody, for coming. Just to reintroduce myself, my name is Chris Pollock. I work for the machine tool business segment for Siemens, and I'm here to talk to you a little about our latest product, the Sinumerik One. So the Sinumerik One is the newest in really a long-run series of Sinumerik CNC controls. And we can honestly say the One is standing on the shoulders of giants. But the One is unique, and it's unique because it's the first digitally native CNC control ever developed and brought to the market. So what do I mean by digitally native CNC? It's kind of a $5 word, right? Well, what it is, this is a control that was conceptualized, designed, and even tested fully in a digital environment before we even dropped the first bead of solder. So this control has the unique ability to be as comfortable in a digital realm as it is in the real world. This new technology is giving us power and flexibility that we have really yet to see in a CNC control at this point. So I can honestly say the Sinumerik One is really the one control an end user would need in their facility. Now, with that, I'd like to explore a little further what we talk about when we talk about this digital side of the control, right? The digital twin or digital native. We hear those terms a lot, and certainly there's a lot of different concepts of what the digital twin is. But in the simplest form, it allows us to take something that we would normally do in a physical environment and put it into a virtual realm. So here we can start to produce product, whether I'm an OEM building a machine or an end user, in parallel to the machine doing other steps. Now, traditionally as an OEM, when they were going to manufacture a product, the process step was very sequential, right? I come up with some kind of a concept, I get my designers involved, and we follow the workflow until I have a product I can actually present to my end customer. However, with that process flow, it is very hard to optimize and streamline it, right? And we want to reduce the time to market. So by digitalizing the control platform, we're actually allowing steps of the manufacturing process to start to be overlaid. So our concept designers can be working on a machine tool, but we can also start developing the PLC simultaneous. So we could literally start creating the machine tool before we've even cast the first part. Obviously reducing our time to market, allowing us to prove out concepts, reducing the capital expenditures we have to put up front to even validate a design. Now, the next step is then leveraging it even to an end customer. So imagine the ability of starting to prototype a concept machine and get functions to an end user where he can start proving out his jobs to see if they'd even be viable. And all that can be done really at the same time. So there's two main areas where you leverage this digital twin concept. There's from the OEM or the integrator's perspective, and then there's from the end user, the end customer. So first we're going to take a look at an integrator or an OEM side. So what we can do is we can actually visualize and build all the pieces of the machine tool and then simulate them to validate the operation and functionality before we even started manufacturing the machine. We can incorporate the full system PLC. We can create behavior models to mimic the I/O. We can go to external devices that will actually allow us to fully control external I/O that's not NC-based axes. So really, there's no step of the process that can't be digitalized at this point. Now, if I'm an end user, I'm going to then take that model that the OEM built. It is now a new value stream for him, because not only does he use it as a design process, but he can now sell this model to the customer with the physical machine tool, and they can start using it for their own process. So they have the ability of importing fixturing, tooling. They can mimic their workflow virtually prior to actually having to do it down on the floor. Now, we have 4 basic variants or variations of this digital twin. And the digital twin in the industry sounds new. However, we've actually been working on this type of functionality for about 20 years now. We started with the Sinutrain package. So a lot of you probably have heard of Sinutrain. We've had it introduced probably a good 20 years now. And that's really the first step into digitalizing your manufacturing floor and creating some variant of a digital twin. So that's going to be used as kind of your entry level into this market. But with the Sinumerik One and its additional capabilities being that natively digital control, I'm now able to step into what we call my virtual machine. And we have different flavors and variations of my virtual machine. We can use it from a perspective of an end user that wants to do just simple simulation, maybe basic programming. But they can then add the full 3D model and the full kinematics of the machine so they can simulate their entire manufacturing process. And if you're a power user, an advanced user, we can actually incorporate this entire functionality and technology directly into NX. So now I can drive the NX module from the CNC control. So as a little bit of an overview, what can we start to do in the digital twin? Well, certainly we can do basic CNC programming, but you can incorporate the full system PLC. We can start to create behavior models to mimic the functionality of the machine, and we can even validate the kinematics and the design and the mechanics to even prove if they're going to work for that application. So how do we do this? There's a lot of people you see creating some variation of a digital twin. And there's all kinds of third-party simulation engines out there. There's one piece of the puzzle that is missing if you don't do it at the control level. And what it is, it's really the brain of the CNC. So we call it our virtual NC kernel. Virtual NCK, you'll hear different derivatives of that. But really, at the simplest form, it is us taking the brain of the CNC and putting it into your PC. Now, why do we need that? Well, the CNC is going to make decisions based on the code you give it. Every time a third-party simulation takes that code, they make an assumption of how the machine is going to move. And guess what? Maybe 90% of the time, that assumption is correct. However, when it's not correct, we could be catastrophic. So for me to truly know exactly the motion path the machine tool will take, I can only do this if I have the full intelligence of the CNC within my PC. Now, what are some of the benefits? Certainly I can use this as an end user for doing basic operation and programming. I mean, what's the key here? We want to keep our spindle running as long as we can, right? A machine tool is a huge capital expense. The minute I shut that thing down for setup or prove out a part or a program, I'm not making money. So we're trying to offload a lot of those steps. So we can use it for part programming. Now I can also use it in scenarios where I have maybe more advanced programming. So let's say you got a user, they're doing families of parts, so they create a parametric program. Or maybe they're doing in-process probing, measure, cut, measure, where they have a lot of logic statements to say, hey, did I make a bore? Is it within spec? It's not. Let me go recut a feature. you can mimic those types of advanced programming right here in this tool. And additionally, and we certainly don't want to overlook this, it is a huge lever in the challenges we have with workforce development. So imagine the ability of actually creating an environment for the students where they can mimic the processes and steps that they would do in front of a machine tool, but that institution doesn't have to spend millions of dollars putting in 30 machine tools. They can have maybe one or two and then have terminals or computer PCs where an end user or student can start engaging with the product and learning how to operate, set up. You can probe in here. Anything you can do in the physical, you can do in this virtual world. Now, this gives you a little idea of kind of how it looks. This is the second tier in those 4 segments of the digital twin. So if I'm running the operate, I can really interface with the exact duplicate of the CNC control. And when I say duplicate, it goes as far as we actually pull data from the real machine tool and read it into the control, and we build the digital twin from the core data that the machine has. So if the machine's been optimized, the digital twin knows it. And that's another big problem when you do 3D simulation in third party, cycle time estimation, right? They think they know the acceleration of the machine, but they really have no idea because you need that core data out of the control. All of that functionality is available here. Now, if the user wants to get to the next step, he can actually mimic his entire process, so I can bring in my work holding. You got a Kurt vise? As long as you have an STL of it, you can bring it right in. I bring in my blank. The blank can be anything. I'm doing cast parts. I could have a cast blank that I'm bringing in. So I can import tooling, fixturing, the whole process, and then go through the setup. Now, let's say I get a weird scenario where I got some giant part, not sure if it's even going to fit on the machine. I can mimic even those processes. I can start to run the simulation even before I quoted the job. Last thing I want to do is bring in a job and realize that I can't actually produce it. So there's so many steps of your manufacturing process chain that you can start to implement this technology. And keep in mind, if I'm not stopping the machine, it could be producing other parts for me. So I can really utilize my capital expenditures the best possible way. Now, you want to get to advanced programming. Now we can take all this technology and start to embed it right inside of NX. Now, what's the difference between what we're talking about with the virtual NC kernel and traditional CAD/CAM based simulation, whether it's NX or anybody else? So normally you're using this common simulation engine. So you're driving everything down and then figuring that a FANUC's going to process data the same as a Sinumerik, the same as a Heidenhain. Once you bring in the brain, now we know exactly how the Sinumerik's going to behave. So again, if there's any discrepancy, we're going to know that. And this is downstream simulation, so it's truly running the G-code programming that's been posted. So if there's post errors, you're going to know it. If there's anything in that process that you normally wouldn't have caught till you were on the floor, you're going to see it here. So this gives you a nice little video where you can start to see what it's going to look like in that interface. So you stay within the CAD/CAM programming environment. When I launch it, it brings up the control interface there on the far left. And then I'm actually driving it from that control interface. So if I needed to go in and change different data points, I can actually run and move around the NX model from the control. Now this is, I would say, the highest level, and then it's going to fit different chains for different users. So with that being said, I want to thank everybody for listening to me ramble on for a few minutes here. I also want to invite up Vivek Furtado and Dave Morley to join me. I understand we're going to have questions.
So happy to take you into the exciting world of digitalization. So Chris already talked about some portion of it. Dave and I will take you a little bit more deeper into what Siemens has to offer here. So our focus today will be basically starting from the engineering and planning side all the way to manufacturing and execution. And having said that, we have different focus elements in our portfolio. So what Chris Pollack just talked about was what we call the smart virtual machine or the digital twin. And you have seen the benefits it can provide to a machine tool builder from an engineering and also from a new business model he could have by so-called reselling of digital twins. So this technology is really enabling new business models. So what we'll further delve in today is also our category, what we call smart machine, where we'll go into different elements on the machine level or on the edge level. But today we have really exciting news for you, and I'll hand over to Dave Morley to reveal more.
Yeah.
Go ahead, Dave.
Thank you, Vivek. So yeah, thank you everybody for your time here. And we're very pleased to present for the first time publicly our new portfolio offering with the name of M-Center. The idea of our product portfolio M-Center is supporting the shop floor activities in terms of tool management capabilities, NC program management functionality, as well as machine connectivity, machine monitoring, and optimization, and also fitting in and leveraging other components of our portfolio. So M-Center, primarily around at least the tool management side. I'll talk about that first briefly. So in terms of a tool management software application in a manufacturing environment, it can be kind of a misunderstood term. I mean, CAM systems have a tool management capability, machine tools do. We do it a little bit different. So we take the data that's already there, essentially in the CAM world and inventory management and the other systems, and we try to bring it all together to assemble, build, and put tools to the machines in time where they need to be by making a lot of connections and gathering a lot of data and intelligence. What you typically see, though, in some cases in terms of a tool management application, there's a lot of time lost or potential time lost for looking for tools, assembling tools, not having the right tools defined that need to be built and measured on a presetter and put to the machine in time. They could even be not even ordered. They could be in the database, but you may have no inventory on hand. So bringing all this together in a centralized tool management way is extremely beneficial. Kind of like Chris was mentioning, quicker to market. You want the machine to keep running, spindles turning. If the tools are built and line side ready for the next job, the spindle will stop as fast as you can change the tools. So very, very minimally. And next slide. So M-Center. So we're ensuring the data, making connections to various softwares and systems in place via our baked-in APIs. It's also reducing setup times, of course, by providing the information to the users who need it and consume it, whether you're in the tool crib, the tool room, or in the CAM area looking for particular tools, or even designing new tools to order and place into inventory. And optimize the resources based on machine data insights. So when we're looking at the machine tools, understanding how many parts they're producing, when the job will be complete, and when the new one will come, what tools need to be replaced in the machine at what time, how to transfer the NC program over to the machine when the machining is done. All that is available leveraging the M-Center platform. Next slide. So I kind of mentioned some of the silos of data, like on the inventory management side. An ERP system will have inventory management, a tool crib will have maybe some different data. The CAM programmers definitely create their own tooling in most cases. So there's a lot of different silos of information in terms of tool data. So bringing this all together, and I kind of like to refer to it as the symphony playing from the same sheet of music, essentially. So all this information is shared, centrally located for everyone to consume. And ideally, keeping the spindle turning is what's most important. Next slide. Okay. So yeah, that's all I would say about M-Center Vivek on Smart Machine.
Thank you.
Yeah.
So let's move on to more of the, say, manufacturing execution side of things. I'd like to share some highlights with you over there. One of the, it's not a new product, it's been about 2 to 3 years since we launched it. It's our, what we call our Sinumerik Edge or industrial edge for machine tools. So we realize more and more that to leverage data out of the machining process, you need to pull out data at a very high frequency, right? And often what happens when you start pulling out data at a high frequency, it impacts the controller performance. And so what we have done is we have built a bridge between this edge processing capability and our controller, so there is no performance issues with that in that respect. So we can sample up to 100,000 hertz without affecting the controller performance. So we can have access to different kinds of data, alarms, machining information, tool path, and so on. And I'll show you now what we can do based on this data. You might be interested to hear, okay, what are you going to do with all that data? It's millions of data points that we are able to take out to the edge box, and also we can process this in our cloud platform, which we call MindSphere, as many might have already heard. So here's one interesting use case. Now, imagine that you have an edge box which is really streaming out, capturing data high frequency, and what we can do is we can set thresholds based on tool path, torque, whatever values you want to do, and what it can do is it can watch or monitor if you're passing these thresholds or not. So that means if you have defined limits for a certain quality of a part, so this is able to monitor quality in real time. So you could say, okay, this part is good, bad, or send out notifications to the operator or whatever you want to do to influence the workflow. Next use case is also we can kind of take a fingerprint of the machine. As a new machine typically has a good fingerprint, and based off several tests, what we can do at the beginning of a shift, whatever, we take different values, whether it's parallel axis or circularity tests, and based off that, we can say, okay, this machine right now is in a good condition, producing good parts. But what happens during during a period of time, this could just go down, and this is able to monitor when these thresholds again go down, and again send out notification to maintenance that this ball screw is faulty, or whatever part needs to be changed. So this again is I think really good use case, getting data and acting upon the data. And here's some new apps that we have. This is basically a camera-based app, also working with the industrial edge, as well as our cloud platform. So what we can do here is we use AI in the cloud to take data from what the system has learned, and the use cases we have is, for example, the workpiece holding, right, in the machining area. So if the workpiece is not positioned properly, so you could actually, through machine learning and a learned model, which is again operating on the edge, you could raise an alarm and saying, hey, there's some issue there. The operator might have left something in the machine room, and it will indicate these alarms if there's something not right. What we can also do with this is monitor the tool wear or tool buildup. So if you have also there a certain threshold what you want to define based on your requirements, you could also set an alarm over there. What we also have is we realize that we need a lot of, say, input from the manufacturing to improve maybe the program, what's the output of the cam. So what we can do is we could actually overlay information from the real machine and the program path, and we could say, hey, where's the fault? And you could say, okay, what you can see here, for example, is velocity profiles. Velocity profiles impact, on one hand, the cycle time of how fast your product is produced, but also surface quality. So looking at this, you could go back and optimize your program and saying, okay, this is where I need to get better or improve productivity. Here's another example of this analyze my workpiece toolpath, and this is a PC-based tool which can bring information together from your CAM as well as from the machine. One more example where we bring again technologies together. Here we have technologies of the digital twin running in real time on the industrial edge. So what this basically does is collision monitoring in real time. So you could actually have the machine stop if it sees a collision, because the digital twin is basically, kind of think of it, it's looking a little bit into the future and giving any signal if there's any collision that's happening. So it's talking in real time to the machine, and thereby avoiding any critical situations, but also in situations where the operator is blind and not being able to see behind some obstruction, so that he could see in his monitor where the axis or the spindle is. So what I've shown is a lot in the, say, digital world, but we also have something called the adaptive control. So you can do this much optimization in the real world, but in the virtual world, but in the real world, you have, say, I would say real-time issues and where you can't foresee, right? So for example, material hardness variations. So you could have material hardness variations. You could have your tool tool tip wearing out faster. So adaptive control takes care of this in real time. In basically, what it does, it accelerates or increases the feed rate to reduce the cycle time. Also looks at the tool to have a constant tool wear to increase your tool life as well. Here's an example where I put everything I talked together in one slide, right? So you can see on the left-hand side, basically the output of your CAD. Now you have your post-processor sending out the CNC program, and this is what I described. We have now the digital twin, and the digital twin you can really see, hey, what's it doing? Is it there's some crashes? Is the part being machined right? And here, so you can see the separation. This is the virtual world, as we call it. You can close the loop without having touched the machine, right? You could actually optimize, on that level. And once you're sure in your virtual world that you want to go ahead, you could, have the program put to the real machine, and the real machine would machine the part. I talked about edge. We could get out data from the edge, do machine condition monitoring, and we also have machine monitoring based on our cloud-based platform. And with that, we have really a closed loop from the real world back to the virtual world to improve overall productivity based on real-time parameters from the production. And in the end, this is a continuous improvement process where all our technologies, and Vince is going to be talking later about how all these elements are going to fit together as part of our Xcelerator portfolio. And that is our objective, really, to not have standalone products, but integrate not only our products, but third-party products in one, digital thread. Yeah, Dave, any further comments from your side?
Yeah, I think you hit the nail on the head from my perspective. So, from my side, our machine tool digitalization portfolio primarily focuses, in my world, on the subtractive side of things, but there's also what I've seen a big interest in the additive side of things. So joining us also next will be Tim Bell from the Additive Manufacturing element.
Again, I'm Tim Bell. I'm the head of additive manufacturing for Siemens Digital Industries. Siemens is broke up into a lot of business units, as you can imagine, and the additive manufacturing is considered a horizontal as we support all of the vertical markets, everything from aerospace to battery to you name it. Almost every company in the world is touching additive manufacturing in one way or another. Not all of them have figured out how to leverage it yet. So Siemens is taking our years of experience and we're helping with that. So we talk about digitalization a lot at Siemens. And what is it in its simplest form? And it's connecting the virtual and the physical worlds. And there's no better technology to leverage this than additive manufacturing. If you think of additive, it was the first component manufacturing technology that was purely digital. You could never print a part from a drawing. you had to have a digital format to be able to produce the part. So it just makes sense that digitalization and additive go hand in hand. So why Siemens and additive? You know, Siemens does a lot of things, but why an additive? And it's pretty simple. As we consider this a company core technology, meaning we are a supplier of end-to-end software, automation, digitalization solutions, but we're also a user. Over 15 years of AM experience in power generation, aerospace, and automotive, but I think more importantly is the number of machines we have globally. With our sister company, Siemens Energy, they run 75 powder bed fusion machines 24/7, producing gas turbine engine burners, swirlers, and some turbine blades even that are in operation. That's a big feat. Some of the aerospace companies have gotten there, but the energy guys have been able to leverage this much faster. So the question is why? I have given a presentation on many occasions, and the name of the presentation is "Just because you can print it doesn't mean you should." There are many reasons why not to print a part. There are many reasons to print a part. Reimagining products, reducing weight and material. I'll talk a little bit about some of the projects we have going on with that. Scan to a product. The military has millions of part numbers that they have no drawings or models for, but we can scan those and reproduce them with 3D printing relatively easy, depending on the material. Expanded performance. That's the biggest takeaway or driver for advanced companies doing braking technology components is performance, whether it be in heat exchangers, whether it be in efficiency of a manifold or hydraulic system. Accelerating innovation cycles. Beautiful thing about additive is you can iterate, you can fail fast, you can reprint the part fast. What I'll show also is how Siemens has alleviated that, because to fail fast, you're actually wasting machine time. You'd be better off to fail in a computer. Rethinking business, industrialization, mass customization, mass personalization. You can have a batch of 1,000 parts in a 3D printer, and every one of them could be the same, yet have each one of your names on them, and it doesn't change the cost. So there's a lot of reasons. BMW actually had a system online. If you bought a new Mini, you could go on and customize internal interior components and print them with your name or whatever you wanted on it. It was cool. They dropped it, but it did it for a few years. Inventory, on-demand printing. This is a huge thing that Siemens, again, company core technology. Siemens Mobility makes trains, and our trains are everywhere around the world, right? Now imagine trying to inventory those parts everywhere in the world. Siemens went on a mission to say how many of the parts in our inventory could be printed on demand, and it ended up being 900 part numbers within the first 2 years. They figured out printed on demand, and then they placed print hubs, small shops, strategically around the world to support that, to print on demand, get it to the customer the next day. It was huge. These are things that don't make it into the media that Siemens is revolutionizing additive around. Reinventing manufacturing. Everybody crosses their arms the same way. Cross them the other way. Change management is the biggest thing slowing down additive, because we have to reinvent how we do things. It's not a bad thing. Now, we talk about where does additive make sense? Well, if you've priced a machine and talked to anybody that makes parts, they're expensive machines. The components seem to be expensive, so it has to be a total value. And it's not going to be, you're never going to go and print a part that you could turn on a lathe for $1. Doesn't make sense, right? You're going to go for leveraging the technology for performance, for life cycle, for sustainability, and I'll show you a slide on that as well. At Siemens, being the giant that we are, we have multiple ways that we support additive. Value-added services and designing factories, and I'll show you a virtual factory. Finance, people don't realize that we're also a bank. I have a facility in Charlotte, I have lots of machines, they're financed through Siemens. We've actually helped a lot of machine tool builders here in the additive space that are smaller, that can't afford to lease a machine to somebody, to leverage Siemens as the leasing entity. So we have our fingers pretty much spread out. Then we have our end-to-end software solution, so I'll talk about in the next slide, and then our automation technology, and I'll touch on that as well. So end-to-end software solutions, what does that mean? In essence, we have looked at our tool chain of software and found that all these pieces can be connected, allowing manufacturers to stay in a software package and do their job. And we're proud to have Vince here today, who's going to talk about the software in detail. But from an additive space, you have order management, generative engineering. That is a big area of growth. Using the computer to do the actual design. Stop letting people design parts. If you come by our booth, you'll see a duct from an HP printer that has a tongue sticking out of it. It's the oddest thing you've ever seen. I would have never designed that, but using CFD to optimize flow and then wrapping surfaces around it and then printing that, it's an optimized duct that increased the efficiency of the printer by 23%. And the simulation tools showed the same thing. So we were like, yes, simulation worked. Build simulation is a big thing in additive. You have a lot of failures because it's a little bit of a black art. There's not a lot of simulation tools, but Siemens has tackled some of these, especially for powder bed fusion, specifically laser powder bed fusion, working with EOS and a lot of these builders to understand the failure mechanisms, build these into build simulations so that you can print the first part right. I worked for the company that bought the very first metal 3D printer in the US, and at the time when we'd quote a part, customers would just be overwhelmed. And we'd say, well, sorry, we're going to have to print 10 to figure out how to get one good one. And then as we learned and we bought more machines, we got to 8 for one good one, 6, 4, 2. And that was a long time of tribal knowledge. And since then, GE purchased the company and prints fuel circuits with it. But the point of this is fail in the computer. Don't fail at the machine. $200-300 an hour machine time, you can't just print and waste all that material. You'd rather fail in the system. Scheduling, all the connectivity that the digital team talked about, connecting all these machines to an MES system. Shop floors today, we see a lot of MES systems, we see a lot of connectivity here, but we're still not making it back to the ERP well. So we've got to get the shop floor to the MES to the ERP because supply chain needs to know more than anybody if the spindle's turning, if the parts are printing, and that's kind of where we're headed now. Now, if we talk about true digital twins, and this is an application that you'll probably enjoy, but we had a customer, there's a company here called EOS. They're one of the longest standing powder bed fusion manufacturers. They had a customer come to them and said, hey, we need like 60 machines. EOS was like, yes, $1 million a piece, we'll take that order. Well, they challenged them and said, but you've got to ensure that these 60 machines meet our targets, our production numbers. And EOS says, we can't do that. We can spreadsheet it out and do our best. Let's go talk to Siemens. So we used our digitalization tools, specifically Technomatics, Concept Designer, Mechatronics, and we mapped out the factory floor with all the machines, with the AGVs, with powder handling, with robots and CNC machining, went through it and found that it really wasn't 60 machines. It was something like 38 or some odd number. EOS wasn't happy, the customer was happy. This factory has been built. It's in Asia. They're not letting anyone know who it is or where it is, but that's okay. At the end of the day, what you'll notice is when you start running the simulations, you can take this as deep as you want, all the way down to what Chris talked about and the digital twin of the control and the kinematics and the multi-physics of the machine. Keep in mind, you've got 60 machines and you're simulating PLCs and I/O and motors and drives. You need a lot of computing power. So typically what we do is we do one and then just duplicate the cycle time across them. But what you'll see here is doing a utilization, the printers are all good. The printers are all green. They're doing well. Well, we start looking at, okay, what about the unpacking stations? Well, I don't think we need 20 of them. So you're now able to visualize this, and your manufacturing engineers are able to go through and virtualize this factory to a degree of confidence. I've set up 6 factories, and it's always been on spreadsheets and PowerPoints and doing it all the long way, and you get it done and you go, shit, we should have moved these over here. Here you can do it virtually. What's really cool about it is we've taken this to the next level, and we've added AR and VR in here where you can actually walk the plant floor. So this has all been done in additive to start because it's all digital. All the tools are digital. So what you see here is we printed out the machines, printed out some people, and now you can navigate through the shop. We have customers who want to use this tool to have a central engineering location and be able to visit any of their factories virtually. And they're all additive, small factories, so it's an easy job to take off with. This is absolutely the next generation of digitalization, and how do we leverage this, and it's better planning. What's really interesting about it is it doesn't matter if it's automotive volume or if it's internal AM workshop. There's still value in virtually setting up this factory, running it through the paces, understanding the failure modes, and planning accordingly. We're here with our folks in the automation. You see a lot of automation in here. And Siemens took a really hard stance on what technologies and additive we were going to support. And it was powder bed fusion, material or binder jetting, DED, or material extrusion. The bottom half, those are CNC controlled. That's what you see over here. The top half, they're PLC and IPC controlled. A lot of 3D printers today are built by companies who are software or process experts. They're not machine experts. We see a lot of these great machines, and they'll take them into GM and set it down, and GM goes, oh, that's cute. I'm not going to rely on that for 24/7 production. So they push back on them and say, look, go to Siemens or go to whoever and get an industrial PC in there or get a PLC in there. And that's where we're at today, is trying to help these manufacturers. And part of the problem is this eye chart of all the things that we offer, and we start getting into the depths, and we have controls that can take and control the smallest machine up to, if you're familiar, there's a machine called the jointless Hall printer. It will print a metal part 30 feet by 20 feet by 12 feet high. It's an Ingersoll machine with a Sinumerik control. It's the largest metal 3D printer in the world. And it was only capable with the Sinumerik control. It's so massive, and there's so many things going on. And it's a unique process that's very, very specific additive. CNC controls are for more of your DED, your material extrusion, where powder bed fusion and binder jet are more PLC or IPC driven. Today, there are about 350 industrial additive manufacturing OEMs. Siemens is actually in over 120 of those machines today. And it's not by coincidence. It's because we understand digitalization, we use the technology, we're not afraid to jump in, even with the small companies, and say, here, we're here to help you. And that brings me to what we've kicked off this year. The Additive Manufacturing Horizontal decided Siemens is amazing at PowerPoints, we're amazing at marketing, but we're actually better at doing shit, if you will. Excuse my French. In doing so, we decided, you know what, we need some AM hubs around the world where we don't just show things, we do things together, and we do things on a collaborative effort. I'm in charge of the one in Charlotte, North Carolina. It's actually the front runner in a new model that Siemens has taken on, and it's a full collaboration. I came to Siemens about 4 years ago from small businesses. I've done 4 startups. I've actually helped found a couple of the companies here. And I went around and we got interest from all these different Siemens business units that had the most amazing, intelligent people around the systems. And we brought them together in a single place called CATCH, the Charlotte Advanced Technology Collaboration Hub. At CATCH, it's an innovation space to help accelerate the industrialization. Everybody's on this path to industrialize additive, and they all think they have the reason or how they're going to do it, but I think together, as a collaborative effort, we can do this much faster. At CATCH, we offer a lot of services to big enterprises who want to get into additive. You wouldn't believe clothing manufacturers who come to us and say, hey, we use all of your hardware and software for our clothing lines. How do we leverage additive? So we sit down with them. We help them design for AM or find the right printing technology or modality, as we say. Development of specific automation or software tools. Additive poses new problems that we're not used to, and the biggest problem is you are creating the raw material and the finished geometry at the same time. So you're responsible for the material properties, chemistry, physical properties, strength, life, all of these things. You don't have the tools to know whether it's there, so inevitably we cut everything up. We print some, we cut them up, we look at them, we print them, we cut them up, we pull them. We're working on using edge computing and some machine learning to be more predictive about these things. We're actually involved in a lot of material development, and most importantly is the development of the business models. This is where over the last 20 years I've seen a lot of people buy printers and not make money with them and then scrap them. The whole program gets scrapped. I used to joke that the only people making money in additive was the material and the gas suppliers. Well, it's starting to change. People who are printing parts are making money finally. Some of the projects that we do at CATCH, decarbonization projects, this is a component where we're taking a gas turbine engine. As we all know, Putin shut off a lot of gas to a lot of people that don't have the proper resources to make energy. Called on us and said, what can you do? We got together and we said, you know what, we can 3D print a microreactor to take the place of the combustor in a gas turbine engine and create a fully efficient generator to put in certain places around Europe to help with this. There's a lot of politics in this, so I'm not going to tell you we're printing yet. The next one down, locomotive waste heat recovery system. This one is amazing. Internal combustion engines are not very efficient, as we know, but we've designed and we're printing recuperators to go on the exhaust of the diesel engine to take that heat and generate more electricity with that heat. Puts the diesel engine somewhere around 95% efficient at that point. Sustainability projects. These are the fun ones from my perspective because there's a lot of problem with raw materials today in the additive space. If you're familiar with electric vehicles, traditionally a car would have about 100 kilos of aluminum in it. The newest cars have 600 kilos of aluminum in it. Where do you think all this aluminum comes from? It doesn't come from here. So we're doing a lot of things like taking used motors, crushing the magnets and reprinting new magnets from them in different geometries and different forms. Magnets aren't very recyclable in traditional methods. Engine components. We have literally taken big companies like Siemens and GE in the gas turbine engine world. They have boneyards full of engine parts that are nickel-based alloys that they know today came. We're having a nickel shortage. So the first thing they did was come to catch and say, how do we recycle these blades back into new blades? We figured out a novel process to convert big, giant Inconel parts or nickel-based parts into powder and then reprint them into new parts. A lot of digital materials and creating the data-driven framework to detect anomalies. We have a printer set up in Charlotte now where we take a picture of every layer and then we actually feed that information into NXCAD and we build a 3D model as we're printing it in the real world. As we're doing that, we can detect anomalies. Oak Ridge National Lab spent about 10 years building a defect database with every additive process known to man, every material possible. We're actually putting that database in an edge device, and the system is actually looking at that database. Are these known defects? Can it make a decision? The world in additive has chased closed loop control where they want to find the problem and go back and fix it. We can't do that. We've got to be more predictive about this, and we have the tools to do it. This is an interesting one that we're printing circuit boards. Yeah, they mass produce them in millions of quantities, and we would never compete with that. But think about short runs, prototypes, problematic, or we've been working with the government on wearable sensors. If we can monitor our soldiers and monitor their health based on something sewn into their uniforms, we can do a much better job of protecting them. And we're doing that through 3D printing today. All of our tests are done on drag race drivers because we can collect so much data in a 6-second time frame of extreme situations. And it's been amazing, the data we've collected. This is a collaboration with a company here called Desktop Metal. Traditionally, a material called MAR M247. It lines the inside of a combustion chamber on a gas turbine engine. It's the hottest area in the engine. The material is only castable, and the fallout from the casting is huge. People have been trying to 3D print it for about 15 years, and very unsuccessfully. And we're proud to say that at Formnext this year, we'll reveal that we've successfully 3D printed MAR 247 from used engine parts. So we're not even using new material. And they'll go into a test rig in probably December. We'll wrap it up here. We have an interesting project that we're working on called SCAR, and it's an autonomous repair robot. The idea behind this is the US military has entire depots full of high-value components that are out of service life. They don't have a repair process for them, and it requires endless hours of a manufacturing engineer to take a component, find the model, create the process. Through a lot of the work been done with the Sinumerik team, we can actually take a damaged component similar to like a turbine blade, scan it, compare that to the original model, and automatically generate G-code to machine the damaged area away, reprint it, and then finish machine it. And we're doing this on a robot that has a tool changer. So it grabs a scanner, it scans the part. It grabs a milling spindle, mills it away, and then different types of printing technologies. The Air Force is pushing us very, very hard to get this done fast, and we're like, we're not going to get there fast. We've proven it out with CCAM in Connecticut. We've done a lot of autonomous repair using CNC control. Chris brought it up of running NX in the control, and that's how we've been able to do it, is feed the point cloud data in from the scan and have NX do all these comparisons. So with that, at Catch, we like to say, the old adage is true: if you want to go fast, go alone, but if you want to go far, go together. And that's why we formed the Collaboration Hub. And we know that you're working with OEMs and end users and ourselves, we've got the horsepower to solve a lot of these problems. And with that, I'm going to introduce Vince Paradise. I appreciate your time. Sir, if you would be so kind.
So thank you, Tim. Thanks for that introduction. And I have to say I love his enthusiasm for additive. I guess it's one of those topics that people get really do get enthused about. My role is slightly different. I actually head up the development of NX CAM for Siemens and the software side from SW. I did actually have a team within that group for a while. It's now with a colleague of mine that was involved in 3D printing, in multi-axis 3D printing. I still look after the development of the CAM robotics side of that's often used in 3D printing. So I still have an interest in that overall space that Tim was talking about there. So I've been given the task here, and I'm glad to do so, to talk about how we bring all this together. We have a massive range of capability. We've talked about some of it here today. You see all the equipment here. There's so much software in the equipment. It's obviously digital. I'm from the software division, SW, and we have lots and lots of obviously software there, all digital. We talk about the same themes. Digital twin, you've heard lots today. Digital thread is very dear to us too. So we're sharing more and more common themes and common concepts. And I think as Siemens, we clearly have an opportunity, a massive opportunity, and actually an imperative to see how we bring this together, how we bring it together in a common business platform that our customers can appreciate. How do we connect the pieces together properly so we don't duplicate, but we can connect, so our customers can get maximum value from everything we can bring together in one sense together. So Xcelerator is a growing initiative that's going to spread and be adopted across many more parts of Siemens as we go forward. You'll see this. And basically it's setting up to be, if we look at some of the concepts here, I'd really just talk very briefly about this, and then I'll go on to talk about how we're showing some of this on the software booth that we have. Really, the key elements here that I'll talk to summarize this very simply, is we have a massive range of software, portfolio of software. It covers all sorts of spaces. Modularity is very, very important. Carefully selecting the right products that we have within this portfolio is important. Includes services, a lot of hardware, of course, and IoT. A lot of software across all of that. So a key theme is that portfolio, wide-ranging portfolio that we have, that we want to bring together under this common business platform that we're calling Xcelerator. Secondly, the ecosystem. We have a massive range of partners out there. I work with many in my area, in the software area, the CAM area. I work with machine tool builders and vendors and so on, obviously the controller vendors are good examples. I work with my group with the cutting tool vendors, for example, for lots of reasons. For us, we want to test our machining software, and working with the cutting tool vendors makes a lot of sense because they want to test their cutting tools with my software, which is being used by some of their big customers too. So we have a lot of commonality with many partners who want to share the same customer base, and our customers want to use not just our software, but often those best-in-class components that we don't sell, like the cutting tools, and maybe software components that we don't have that are very complementary. So we have a very open system that enables us to work with partners so they can embed their software into ours. We can't do everything ourselves, but that builds an ecosystem that is a win-win. It's a win for our customers, it's a win for us, and it's a win for our partners, because they can reach markets they wouldn't otherwise reach. So the ecosystem is a critical part, a growing part of this business. And it's getting bigger and bigger as we go onto the cloud, and we have things like hyperscalers, people who can help us propel that software to many users using the cloud. We have more and more partners coming in that are skilled in those sort of spaces where we aren't going to do those pieces ourselves either. And then growing, this is perhaps a new area that's growing, a marketplace, because we have within this sphere of operations in the business, we have a lot of things that our customers want to come and see. They want to get information, they want to learn, maybe they want to download information. Maybe they want to buy components so they can buy them too, from a marketplace concept. And so that's what we're building out more and more. One of the components I'll show you in a minute that I have for my space, it fits within that marketplace, and I'll come back to that and show it later. So these are the three key elements that we'll point to as we build out this common business platform that we can all get behind from our various business segments. And you'll see this as a common message. And underneath it, those common themes of things like digital twin, digital thread, you'll keep seeing that come through. So, in action, what are we doing here today? We have a booth, and I'll talk briefly about what we're doing on the booth and what we're showing there that kind of picks up some of this story. So, this is on our booth in the software area, and you'll see here we've taken a component. Actually, it's an electric vehicle. That's topical, I guess. It's a sports vehicle. You see it on the booth. There's going to be a picture of it in a minute. I think there's a picture of it on the previous slide. You see a picture of that vehicle there. So we took the vehicle and we took part of it and said, let's see what can be a challenge for us. And the challenge we took was to take a component that some of you will recognize. It's a steering knuckle, the piece that goes behind the wheel. It's part of the unsprung weight, if you like. It's not sprung off the road. And so the objective here is to make it lighter. Right, so that's obviously an objective for performance cars. You want that piece to be as light as possible. And so we took that part and looked at how we can redesign it. So here we used our technology around optimization, thinking we're going to print it. One of the ways you can optimize the shape is to print it and look at topology optimization. So again, inside NX, we took the part and ran it through our topology optimization. You see one of those pictures there, you see very sort of organic shape appears. Now, that's great, but those organic shapes, I know from machining, from my space, that's pretty hard to machine sometimes. It's a beautiful shape, but how do I hold it? Right? How do I machine it? And so we have another step where we optimize it for manufacturing. What shape should it be? And we just modify the topology one step further to say, now I can machine it, or I can manufacture it, or I can print it more easily. So we take into account how we're going to print it. So that's also an important step. It's not just the topology optimization to say, I've got a part here which is just as strong, but now it's lighter. I also have to worry about how to make it, right? And then we simulate that, of course. All the time we're simulating to make sure it is going to be strong. It's not going to have vibration problems or break. Clearly, it's no good if it breaks, right? It's a critical part of the suspension. And then we go through various stages, validating we actually did meet all the tolerances. For example, when we manufacture it, as I go into machining, we have various tolerances to make sure the shaft is going to fit in the steering knuckle. We printed the component. In fact, we printed 3 of the components. And you'll see if you go onto the booth, that picture there in the bottom row, if I can put my cursor over it, it's very interesting. It's got 3 of those components, and we actually built it around a work holding. So the work holding is printed, right, because I've got to hold this thing somehow, and that's a challenge. So we built 3 of them together around that trumpet shape, which is actually the work holding. We're going to machine that off at the end, of course, right? So designing that, make sure we can hold the 3 parts as we machined it is critical. And then we go into the machining, the programming itself, it's subtractive. So what we're showing here really is an integration of 3D printing metal, with our traditional subtractive business, right through to the shop floor and to the controller. And on the booth, you'll see the information. This sort of setup uses a lot of our software. I'll show you that in a minute. And it's all connected together right down to the machine. In fact, here's some of the software we used. On the right, there's a picture of my software, my group, the machining software, NX CAM, but also many parts of NX in design, optimization, analysis there, Teamcenter. All the stations on the booth are linked together. The data is managed in Teamcenter, right? So we're walking the talk, as we say. It does work. We connect it all together, right down to the connection to the machine tool that we have with the Siemens controller. It's a make-believe Siemens machine, a simulation of one, but it has a real controller on it, and we're connecting to that from Teamcenter with our shop floor connect add-on to Teamcenter. Simcenter for the analysis, optimization. OpCenter is their MES system from SW, and obviously connecting to our colleagues with the Sinumerik. You've heard about the Sinumerik One and all the simulation technology that's on the booth as well, with the VNCK driven realistic simulation that they've got. So using quite a range of software on this setup here. Partners, so that was part of the portfolio we're using. This talks about the ecosystem, the technology partners, and we worked again. It's a very good example of how we had to collaborate. We couldn't build this ourselves. We don't print things ourselves, so we had to work with partners. DMG Mori up the road in Chicago helped enormously with printing these parts. We tried it. We did it in Inconel, we did it in titanium, and we did it in hard steel. So we had a lot of help on that. The actual axle components that goes into the hub was turned, regular turning parts on a track machine. We used cutting tools from water and Kennametal. I talked about our partners in the cutting tool area. ModuleWorks, one of our technology partners we use quite a lot or across the board in various areas, are actually putting in some software here on that simulation system that's running with the Siemens controller on it for photorealistic simulation of that machine tool. Quite a collection of partners here involved, illustrating our ecosystem that I talked about. So this is the last slide, very quickly. Having said all that, it sounds great, but when we go to deliver this, it has to be easy. We have a lot of complicated software to play with. We had a challenge here we addressed, which was to weight reduction. We want to reduce programming time as we do that. We have to make sure that's going to be easy, and that's a challenge for us to make sure the software is going to be easy. It needs to be flexible. Modularity is a big word now. I come from development, and we're talking all the time about being modular. For two reasons. One, we want our customers to be able to choose the modules they want to work with. But also, when we go to the cloud, as we are more and more, you can't carry along a big monolithic block of software. It just won't work on Amazon. It's just too expensive to hold it like that. We have to make it much more modular at an architectural level. So that's a challenge for us too. As we go forward, you'll see our software becoming more modular at those different levels for different reasons. And integration, as I've touched on, we have to integrate and not just use that word. We often, over the years, threw that word out many times, integrated, but it has to work. And you'll see on the booth, we're talking about those connections between those different systems, and the shop floor connecting down to the controller is a key example of us integrating these different elements together. So very quick overview of Xcelerator and how important it is going forward, or now and going forward, in terms of pulling us all together in a common platform, a common business platform to tie ourselves together in all these different industries and the hardware, the equipment, and the software that we all have.
15 minutes time left, just perfectly scheduled for a quick Q&A session, so I invite the rest of the presenters to come up to the stage. If there are questions from the audience, and I'm sure there hopefully are, because there's a lot of information that was presented today, please raise your hand, we'll call on you, and then depending upon who the question might be requested for, we ask that person step up to the stage, or to the microphone. So, fire away.
I've got two quick questions, hopefully quick, one for Chris and one for Tim. Chris, in your presentation, you were talking about how the software can be for OEMs and end users. Based on what you're seeing on uptake or interest in the market so far, is it more for OEMs who are incorporating it into their equipment? Is it more for end users, or is there any differentiation in different verticals, some using it more than others?
So I would say the largest install base currently is from the end user perspective. And I think primarily because the earlier variants were really designed specifically for end user applications. And we've now been able to grow it with the new functionality of Sinumerik One to be able to be leveraged from an OEM side. So the OEMs are now just starting to really see the value of this new concept of manufacturing. And it's going to take a little while, right? Where it's a change in the paradigm shift in how they work, but it's coming more and more. You know, we see early adopters are usually the guys that are always pushing technology. And then it trickles down to the guys that are making more of your mass production commodity-based product.
And the other question for Tim, you were talking about the EOS application, how they originally thought they needed 60 machines, and it turned out to be 30, I think.
Roughly, yeah.
Did I understand that was based
Correct.
on virtualization?
Yep.
I just want to make sure I
Yep.
understood.
No problem.
Thank you. Other questions?
So there's competing forces here. You want to put more functionality together in software, but you want to make it lighter and more modular to run up in the cloud. How are you keeping track of how the software interacts with each other, with the customers, with the various applications?
Do that one? Yeah, really good question. I mean, it's a major challenge, clearly, as we move into a new generation of software that the cloud demands. The only way is really understanding and testing. You have to take these things apart and see how they plug together, understand what architecture is required to be efficient on the cloud, and in terms of how it's hosted and how the users are going to use it. And there are different use cases. I mean, if I'm in, say, SimCenter and I'm looking for very high performance computing, that's a very different requirement than someone who's doing a very more simple task and want to do so at the very lowest possible cost in terms of the resources that are tied up. So we're looking at understanding the software how we have to re-architect it in many ways. We can run our software today on the cloud. I mean, we can lift and shift, as we say, or lift NXCam and run it on the cloud. We do so today for trials and testing. We put NXCam on the cloud and stream it, right? And it's very effective. But the cost of doing that is prohibitive for, say, 6,000 users. The cost of tying up all those Amazon servers and all the repeated servers we have to tie up would not be cost effective. So we have to look at understanding how the architecture should be rebuilt. So you get multi-tenant software, you have stateless software, so we can support multiple users off the same code at the same time. So lots of changes to the software which aren't really a problem to us when we're running on a desktop machine. So we have to test it, and is a key thing. I'm not sure that's the answer you wanted, or good enough.
Other questions?
In the additive manufacturing area, how the software needs input for design. How do you make sure that the software doesn't have the same prejudice that humans had in designing parts? The tongue, for instance, on the HP.
Yeah, the software doesn't care, right? And software team's done an amazing job leveraging HEEDS and some other automation tools that go through scenarios one and after another till it meets all the criteria and the requirements, and then it's dumb. It doesn't matter. Just bing, got the green light, here's the design. So you're not having the prejudice. You don't have, as a designer, I would always think geometry. How do I get the spindle in there? How do I get the tool in there? And with additive, you don't care. You can just be as organic and weird shaped as possible. I think there was a test that you guys did with an aircraft manufacturer to look at using topology optimization for landing gear and reduce the weight by 2/3 or some ridiculous number. And the aircraft manufacturer was like, that is absolutely beautiful, but I'm never signing off on that crazy looking geometry. And that comes down to that whole change management, is it doesn't look like what we're used to, so it's hard to accept it. And that prejudice is very, very high.
They were giving up 2/3 weight gain because of geometry.
Again, we cross our arms like this. We don't like to do it this way.
Questions? Yes, sir.
In the CNC virtual machine tool application, how good is it in predicting like tool wear? If you're training someone and eventually the tool wear gets to you, how do you train someone to visualize that? Oh, I have to change the tool now, because that's usually tribal knowledge.
Yeah, absolutely. And at this point, we are not at a position where we're simulating the wear of the tool or even the load on the spindle and then varying that. I'm sure that's going to come, but we're not there yet. So really, from an educational standpoint, you're kind of showing a perfect scenario. But that's why we still need a machine tool in that environment. We can't completely displace the use of a real machine in that facility. We can just allow more people to interface with the product through the PC, and then eventually you still have to get a little bit of spindle time. You're never going to get away from basic speeds and feeds, cranking a Bridgeport, right? Best way to show somebody what chip load is all about. You always need that step. But I think we're going to get there for sure.
If I may, in
Yeah.
the additive side, everybody's focused on OEE and collecting this data from the machine of on time, uptime, stop, setup. In the additive space, we've done a few things where we're actually monitoring, say, the motor amperage draw for a specific operation. And think of powder bed fusion when they do a recoater and they recoat that powder across there. If that recoater used 2.6 amps for just a dumb number, and this next time it used 2.8, well, now we've got a quality OEE flag that we can address, not just an uptime, downtime address. So it's not anything like listening and, hey, the tool's wearing out or load's going up, but it's trying to be smarter about the tools that we do have. We're already monitoring every single digital 1 and 0 in there. Why don't we do something more with it? And an additive is guilty of data overconsumption, collecting every piece of data from every print known to man. I mean, NASA finally had to write a spec and say, no, this is all we care about, because everybody was just collecting everything. So if we're smarter about it, I think there's ways to get there.
Other questions?
Then in that case, I would like to say thank you very much. That will conclude the press conference. If you do have additional questions or you'd like a little one-on-one time with any of our experts here, we also have a couple other experts in the room. Feel free to stick around for a little bit. We're more than happy to have that one-on-one conversation with you. In that case, on behalf of all of our presenters, on behalf of Siemens, on behalf of myself, thank you very much for being here. Thank you for taking the time out of your afternoon. And we hope you have a very successful show at IMTS. Thank you very much.
Thank you.